Welcome to Chemistry, Acid-Base Neutralization. In this presentation, we explore one of the most important classes of chemical reactions in all of chemistry, the reaction between an acid and a base. From the moment you sip a glass of orange juice and feel its tartness on your tongue, to the antacid tablet that soothes an upset stomach, to the industrial processes that produce fertilizers, pharmaceuticals, and clean water, acid-base chemistry is at work. We will start with the three complementary definitions of acids and bases. We will master the pH scale. We will study acid-base neutralization reactions, the precise stoichiometry of titrations, the shapes of titration curves, the role of indicators, the use of pH meters, and the elegant mathematics of buffers and the Henderson-Hasselbalch equation. By the end, you will be able to look at any acid-base system and predict with confidence what reaction will occur, what the pH will be, and how to design a buffer for any desired pH. The pH scale is the universal yardstick chemists use to measure how acidic or how basic a solution is. pH is defined as the negative base 10 logarithm of the hydrogen ion concentration in moles per liter. The scale runs from 0 to 14 in aqueous solution at 25 degrees Celsius. A pH of 0 is extremely acidic. A pH of 7 is neutral. A pH of 14 is extremely basic. Each step of one pH unit represents a tenfold change in hydrogen ion concentration. Lemon juice has a pH around 2. Vinegar has a pH around 3. Coffee is about 5. Pure water is 7. Blood is slightly basic at 7.4. Bleach is around 13. The pH scale is logarithmic, intuitive, and absolutely central to chemistry, biology, medicine, and environmental science. The first modern definition of acids and bases was proposed by the Swedish chemist Svante Arrhenius in 1884. An Arrhenius acid is a substance that, when dissolved in water, increases the concentration of hydrogen ions, H+. Common examples include hydrochloric acid, HCl, nitric acid, HNO3, and sulfuric acid, H2SO4. An Arrhenius base is a substance that increases the concentration of hydroxide ions, OH-. Common examples include sodium hydroxide, NaOH, potassium hydroxide, KOH, and calcium hydroxide, CaOH. 2. The Arrhenius definition is simple and useful for aqueous solution chemistry, but it is limited to aqueous solutions and cannot explain substances like ammonia that act as bases without containing OH-. In 1923, Johannes Brønsted and Thomas Lowry independently proposed a more general definition. A Brønsted-Lowry acid is a proton donor, a substance that gives up an H+ ion. A Brønsted-Lowry base is a proton acceptor. The beauty of this definition is that it makes the central role of proton transfer explicit. Every acid-base reaction is a proton transfer. Consider ammonia and water. NH3 accepts a proton from H2O, becoming NH4+. H2O donates a proton, becoming O-. So ammonia is the Brønsted-Lowry base, and water is the Brønsted-Lowry acid. NH3 and NH4+ are a conjugate acid-base pair, differing by exactly one proton. The most general definition was proposed by Gilbert N. Lewis in 1923. A Lewis acid is an electron pair acceptor. A Lewis base is an electron pair donor. The base donates a pair of electrons to form a new covalent bond with the acid. Every Brønsted-Lowry acid is also a Lewis acid. But the Lewis definition includes many other reactions, such as the reaction of boron trifluoride BF3 with ammonia NH3. BF3 has an empty p orbital that accepts the lone pair of ammonia, forming the adduct F3BNH3. Many metal ions are Lewis acids because they accept electron pairs from water or ammonia to form complex ions. The Lewis definition is essential in organic chemistry and catalysis. Pure water is not entirely stable. A tiny fraction of water molecules react with each other in a process called autoionization. Two water molecules react to form a hydronium ion H3O+ and a hydroxide ion OH-. The equilibrium constant for this reaction is a special constant called Kw, the ion product constant of water. At 25 degrees Celsius, Kw equals 1.0 times 10 to the minus 14. The product of the hydrogen ion concentration and the hydroxide ion concentration always equals Kw. The autoionization of water is the reason a neutral solution has pH 7. It is also the reason that no aqueous solution can be completely free of both H+ and OH-. The ion product constant of water, Kw, is one of the most important constants in chemistry. At 25 degrees Celsius, Kw equals 1.0 times 10 to the minus 14 with units of molarity squared. This constant connects the hydrogen and hydroxide ion concentrations in every aqueous solution. In acidic solutions, the hydrogen ion concentration is greater than 10 to the minus 7 molar, and the hydroxide ion concentration is correspondingly less. For example, in a solution with H plus equal to 10 to the minus 3, OH minus equals Kw divided by 10 to the minus 3, which equals 10 to the minus 11. Knowing Kw lets us calculate any one of H plus, OH minus, pH, or POH if we know any one of the others. Calculating pH and POH for any aqueous solution is straightforward. pH is the negative log of the hydrogen ion concentration. POH is the negative log of the hydroxide ion concentration. POH plus POH always equals 14. To calculate pH from a hydrogen ion concentration, take the negative log. A solution with H plus equal to 1 times 10 to the minus 3 has pH equals 3. To calculate pH from a hydroxide ion concentration, first find POH, then subtract from 14. A solution with OH minus equal to 2 times 10 to the minus 5 has POH of 4.7, so pH of 9.3. To calculate H plus or OH minus from a pH, use the inverse log. These four operations are the workhorses of every acid-base problem. Acids and bases come in two flavors, strong and weak. A strong acid dissociates completely into ions when dissolved in water. The 7 common strong acids are HCl, HBr, HI, HNO3, HClO4, H2SO4, and HClO3. A weak acid only partially dissociates. The strength of a weak acid is measured by its acid dissociation constant Ka. The larger the Ka, the stronger the weak acid. But even the strongest weak acids are far weaker than the strong acids. Strong bases are the group 1 hydroxides like NaOH and KOH. Weak bases include ammonia and H3. Strong does not mean concentrated. You can have a dilute solution of a strong acid. Acid-base neutralization is the prototypical reaction of aqueous chemistry. In a neutralization reaction, an acid reacts with a base to form a salt and water. The general form is acid plus base gives salt plus water. The hydrogen ions from the acid combine with the hydroxide ions from the base to form water. The cation from the base and the anion from the acid combine to form a salt. For example, hydrochloric acid plus sodium hydroxide gives sodium chloride plus water. Another example, sulfuric acid plus potassium hydroxide gives potassium sulfate plus water. 1 mole of H2SO4 provides 2 moles of H+, so it needs 2 moles of KOH to neutralize. Titration is the practical, quantitative application of acid-base neutralization. A solution of known concentration, the titrant, is carefully added to a solution of unknown concentration until the reaction is exactly complete. The point at which stoichiometrically equivalent amounts of acid and base have reacted is the equivalence point. The point at which an indicator changes color is the endpoint. From the volume of titrant used, its known concentration, and the mole ratio from the balanced equation, we calculate the moles of titrant delivered, and from those, the moles of analyte present. Titrations are used in food chemistry, water treatment, pharmaceutical analysis, winemaking, and clinical chemistry. A titration curve is a plot of pH versus volume of titrant added. The shape of the curve reveals whether you are titrating a strong acid with a strong base, a weak acid with a strong base, a strong acid with a weak base, or a weak acid with a weak base. The classic strong acid strong base curve starts at a very low pH, around 1, and rises slowly. Then, within a fraction of a milliliter of the equivalence point, the pH shoots upward by 6 or more units through pH 7 to a pH above 12. The weak acid-strong base curve looks different. It rises through a buffer region where pH changes slowly. The half equivalence point is special. At this point, pH equals pKa. The titration of a strong acid with a strong base is the simplest and most dramatic type. Hydrochloric acid titrated with sodium hydroxide is the textbook example. The balanced equation is HCl plus NaOH gives NaCl plus H2O. The mole ratio is 1 to 1. Both dissociate completely. The titration curve starts at a very low pH. For a 0.1 mHCl solution, the initial pH is exactly 1. As we add NaOH, the pH rises slowly. At the equivalence point, exactly 1 mole of OH- has been added for every mole of H+. All the acid has been neutralized. The solution contains only spectator ions plus pure water, so the pH is exactly 7. Past the equivalence point, excess OH- accumulates, and the pH rises rapidly. A pH meter is an electronic instrument that measures the hydrogen ion activity of a solution with high precision. The heart of a pH meter is a glass membrane electrode, which develops a small voltage proportional to the logarithm of the hydrogen ion concentration. The meter is calibrated with two buffer solutions of known pH, typically pH 4, pH 7, and pH 10. Modern pH meters are digital, often with automatic temperature compensation, since pH is slightly temperature dependent. They can measure pH to within 0.01 units or better. pH meters have largely replaced indicators in research and clinical laboratories because they are objective, continuous, and applicable across the full pH range. An acid-base indicator is a weak organic acid or base whose protonated and deprotonated forms have dramatically different colors. The indicator equilibrium is Hin in one color, in minus in the other. The color we see depends on the pH relative to the indicator pKo. The pKa of an indicator is the pH at which it is 50% in each form. An indicator changes color over a range of about 2 pH units, centered on its pKo. Common indicators include methyl red pKa5 for weak acid strong base titrations, phenolphthalein pKa9 for strong acid strong base titrations, and bromothymol blue pKa7. Choosing the right indicator requires matching its color change range to the steep portion of the titration curve. A buffer is a solution that resists changes in pH when small amounts of acid or base are added. Buffers are essential in chemistry, biology, and medicine. Blood is buffered at pH 7.4. The ocean is buffered by the carbonate system. The two key components of a buffer are a weak acid and its conjugate base, present in comparable amounts. The weak acid neutralizes any added base, while the conjugate base neutralizes any added acid. The pH of a buffer is given by the Henderson-Hasselbalch equation, one of the most useful equations in all of chemistry. pH equals pKa plus log of the conjugate base concentration over the acid concentration. The Henderson-Hasselbalch equation is the master formula for buffer calculations. pH equals pKa plus log of the conjugate base concentration over the acid concentration. The pKa is the negative log of the acid dissociation constant. The equation is derived from the Ka expression by taking the negative log of both sides. It is valid when the concentrations are much larger than the amount of acid or base added, and when the pH is within about 1 unit of the pKa. For an acetic acid acetate buffer with pKa 4.74, mixing equal moles of acetic acid and sodium acetate gives a buffer of pH 4.74. The equation lets us design buffers for any desired pH by choosing the right acid-base pair. Buffer capacity is the quantitative measure of how much acid or base a buffer can absorb before its pH changes significantly. The buffer capacity beta is defined as the number of moles of strong acid or strong base required to change the pH of 1 liter of buffer by 1 unit. The buffer capacity is maximum when the pH equals the pKa, because the slope of the titration curve is flattest there. A buffer is most effective within plus or minus 1 pH unit of its pKa, and is essentially useless outside plus or minus 2 pH unit. Buffer capacity also increases with total buffer concentration. Designing a buffer means choosing a pKa close to the desired pH, and choosing a concentration high enough to absorb the expected perturbations. Many important acids can donate more than one proton. These are called polyprotic acids. Diprotic acids, like sulfuric acid H2SO4, carbonic acid H2SCO3, and oxalic acid H2C2O4, can donate 2 protons. Triprotic acids, like phosphoric acid H3PO4, can donate 3 protons. Each proton has its own K value, and these are always different from each other. For phosphoric acid, the first dissociation has K1 equal to 7.5 times 10 to the minus 3. The second has K2 equal to 6.2 times 10 to the minus 8. The third has K3 equal to 4.8 times 10 to the minus 13. Each successive Ka is smaller than the previous one by several orders of magnitude. Acid-base chemistry is everywhere. In medicine, blood plasma is buffered at pH 7.4 by the carbonic acid bicarbonate system. If blood pH falls below 7.35, the condition is called acidosis. If pH rises above 7.45, it is called alkalosis. In agriculture, soil pH determines which plants will grow. Farmers add lime, CaCO3, to raise pH, and sulfur or aluminum sulfate to lower it. In industry, sulfuric acid is the most produced chemical in the world. Sodium hydroxide is used in soap making, paper production, and water treatment. In environmental science, acid rain from sulfur and nitrogen oxides lowers the pH of lakes and streams, killing fish. Acid-base chemistry is the chemistry of life, of industry, of the environment, of everything. Let us bring together everything we have covered. Acid-base chemistry rests on three definitions, each broader than the last: Arrhenius, Brønsted-Lowry, and Lewis. The pH scale measures acidity as the negative log of H+. pH plus pOH equals 14. The product H plus times OH minus equals Kw. Strong acids and bases dissociate completely. Weak acids and bases dissociate partially. Acid-base neutralization is the reaction of H plus with OH minus to form water. Titration is the quantitative application. The shape of the titration curve reveals the strengths of the acid and base. Indicators change color near their pKa. pH meters measure pH electronically. Buffers resist pH change. The Henderson-Hasselbalch equation is the master formula for buffer calculations. Polyprotic acids donate multiple protons, each with its own K. Acid-base chemistry is the chemistry of life, of industry, of the environment, of the kitchen, of the bloodstream, of the ocean. Master these concepts, and you hold the keys to a vast kingdom of chemistry. Quiz question 1. What is the pH of a solution with a hydrogen ion concentration of 1 times 10 to the minus 4 molar? pH is the negative log of the hydrogen ion concentration. The negative log of 1 times 10 to the minus 4 is 4, so the pH is 4. This is a moderately acidic solution, similar to tomato juice or acid rain. The correct answer is B. pH equals 4. Quiz question 2. Which of the following is a Brønsted-Lowry base, but not an Arrhenius base? The Arrhenius definition requires a substance that produces OH- and water. NaOH, KOH, and KOO2 all contain OH in their formulas and produce OH- and water, so they are both Arrhenius and Brønsted-Lowry bases. Ammonia, NH3, contains no oxygen and does not contain OH in its formula, so it is not an Arrhenius base. But in water, NH3 accepts a proton from H2O to form NH4+ and OH-, so it is a Brønsted-Lowry base. The correct answer is D, ammonia. Quiz question 3. What is the pH of a 0.01 m solution of HCCl? HCl is a strong acid, so it dissociates completely. The H plus concentration equals the HCl concentration 0.01 molar, or 1 times 10 to the minus 2. The pH is the negative log of 1 times 10 to the minus 2, which is exactly 2. The correct answer is A, pH equals 2. Quiz question 4. A buffer is made by mixing equal moles of acetic acid, Ca equals 1.8 times 10 to the minus 5, and sodium acetate. What is the pH of the buffer? When the concentrations of acid and conjugate base are equal, the ratio in the Henderson-Hasselbalch equation is exactly 1. Log of 1 is 0. So pH equals pKa. The pKa is the negative log of 1.8 times 10 to the minus 5, which equals 4.74. So the pH is 4.74. The correct answer is C. pH equals 4.74. Quiz question 5. Which indicator would be best for the titration of a weak acid with a strong base, with equivalence point at pH approximately 9? For a weak acid strong base titration, the pH at the equivalence point is greater than 7 because the conjugate base of the weak acid hydrolyzes water to produce OH-. We need an indicator that changes color near pH 9. Methyl orange, pKa3, changes at pH 3 to 4, too low. Bromothymol blue, pKa7, changes at pH 6 to 7, too low. Phenolphthalein, pKa9, changes at pH 8 to 10, perfect. Alizarin yellow, pKa11, changes at pH 10 to 12, too high. The correct answer is C, phenolphthalein. Problem 1. What is the pH of a 0.025 m solution of HCl? Step 1. Identify that HCl is a strong acid that dissociates completely. So H plus equals 0.025 molar. Step 2. Take the negative log. pH equals negative log of 0.025. Convert to scientific notation. 0.025 equals 2.5 times 10 to the minus 2. Negative log of 2.5 times 10 to the minus 2 equals negative log of 2.5 minus log of 10 to the minus 2 equals 0.40 plus 2 equals 1.6. So pH equals 1.6. This is a strongly acidic solution, comparable to gastric juice in your stomach. Problem 2. How many milliliters of 0.15 AgM NaOH are needed to neutralize 25.0 milliliters of H.200 MHCl? Step 1. Balanced equation is HCl plus NaOH gives NaCl plus H2O. Mole ratio is 1 to 1. Step 2. Calculate moles of HCl. Moles equals molarity times volume in liters, 0.200 times 0.0250, which equals 0.00500 moles, or 5.00 times 10 to the minus 3 moles. Step 3. Moles of NaOH needed equals the same, 5.00 times 10 to the minus 3 moles. Step 4. Volume of NaOH equals moles divided by molarity, which equals 5.00 times 10 to the minus 3 divided by 0.150, which equals 0.0333 liters, or 33.3 milliliters. So we need 33.3 milliliters of NaOH. Problem 3. A buffer contains 0.50 m acetic acid, Cat 1.8 times 10 to the minus 5, and 0.30 m sodium acetate. What is the pH? Step 1. pKa equals negative log of 1.8 times 10 to the minus 5, which equals 4.74. Step 2. Henderson-Hasselbalch. pH equals pKa plus log of acetate over acetic acid, which is 0.30, divided by 0.50, which equals 0.60. Log of 0.60 equals negative 0.22. Step 3. pH equals 4.74 plus negative 0.22, which equals 4.52. So the pH is 4.52. Notice that we are within 1 pH unit of pKa, so the buffer is effective. Problem 4. What is the pH of a 0.10 m solution of ammonia, NH3, Kb equals 1.8 times 10 to the minus 5? Step 1. Write the equilibrium. NH3 plus H2O is in equilibrium with NH4 plus OH minus. Kb equals NH4 plus times OH minus divided by NH3. Step 2. Set up the equilibrium table. Initial NH3 is 0.10. Change is minus x. Equilibrium is 0.10 minus x. NH4 plus and OH minus both start at 0 and end at x. Step 3. Substitute into KBB. 1.8 times 10 to the minus 5 equals x squared over 0.10 minus x. Assuming x is much smaller than 0.10, this simplifies to x squared equals 1.8 times 10 to the minus 6. So x equals 1.34 times 10 to the minus 3. Step 4. This x is the OH minus concentration. POH equals negative log of 1.34 times 10 to the minus 3, which equals 2.87. So pH equals 14 minus 2.87, which equals 11.1. Problem 5. Phosphoric acid, H3PO4, is a triprotic acid with Ca1 equals 7.5 times 10 to the minus 3, Ca2 equals 6.2 times 10 to the minus 8, Ca3 equals 4.8 times 10 to the minus 13. Calculate the pH of a 0.10 m solution of H3PO4. Step 1. The first dissociation dominates because Ca1 is much larger than Ca2. So we treat the problem as a monoprotic weak acid. H3PO4 is in equilibrium with H plus H2PO4 minus. Step 2. Setup. Initial H3PO4 is 0.10. Change is minus x. Equilibrium is 0.10 minus x. H plus and H2PO4 minus both end at x. Step 3. Ca1 equals x squared over 0.10 minus x. Assuming x is much less than 0.10, x squared equals 7.5 times 10 to the minus 4, so x equals 2.74 times 10 to the minus 2. Step 4. pH equals negative log of 2.74 times 10 to the minus 2, which equals 1.56. So pH is approximately 1.56. The contributions from the second and third dissociations are negligible by comparison.